What are we thinking of? So what are you thinking of? What kind of a mathematical structure are we thinking of? What kind of a set structure are we thinking of? It is the intersection of the two budget sets. It is the intersection of the two budget sets. It is the intersection of two convex sets. So next question is the intersection of two convex sets also convex? It is, right? So the set of consumption bundles which were affordable under the previous prices and the set of consumption bundles which are also affordable under the new prices is also a convex set. It's also a convex set. That is, if X was a consumption bundle which is affordable under both the prices, and if Y is a consumption bundle which is affordable under both the prices, then any linear combination of the two consumption bundles will also be affordable under the two under both the price situations. Right? Is this clear? Right? So this helps us think a lot in ways which otherwise we could not have been able to think of, no, in the standard geometric kind of a way. Right? Okay. Now, yeah.
Coming back to the formula, you said that EX1 and EX2 now, both the companies have different prices.
No, P is the same.
Okay,
P is the same. Yeah? Or, if I allow P1 to be a different consumption bundle, then P1X is a set of all consumption bundles which are affordable under P1. P2 is a set of all consumption bundles which are affordable under P2. The intersection is a set of consumption bundles which are affordable under P1 and P2, both. And then we are arguing because the first set is a convex set, the second set is a convex set, the intersection of two convex sets is also convex, and therefore both the consumption bundles will also, so the set of consumption bundles which are affordable under both the price sets will also be convex. Sure? Is this idea clear to everybody? Right? Okay. Is a set of all integers a convex set? Is a set of all integers a convex set? Is a set of all integers a convex set? Why would it not be a convex set? Because a linear combination of two integers is not always, in general, an integer. 0.5 into 1 plus 0.5 into 2 is 1.5. Is 1.5 an integer? No. So therefore set of all integers is not a convex combination. Right? A set is not a convex set. Can you give me examples of sets which are not convex? Any complementary set of real numbers? Even numbers. Is a set of even numbers a convex set? No. Because the linear combination of two even numbers is not necessarily an even number. 0.5 into 1, 2 plus 0.5 into 4 is 3, which is an odd number. Right? So set of even numbers or set of odd numbers are not convex sets. The set of no, but what is the set which don't have real numbers? So what are the numbers that are not real? That are complex numbers, no? Complex numbers actually are numbers which so there is a larger set of numbers. So if you take the real numbers out, what remains is the complex numbers, right? But is a set of all complex numbers a convex set? It is. No? It is, because you can always, any linear combination of complex numbers is a complex number. So it is actually not true. Any other example in your day-to-day life? So if I take, say, if I take a set of all, give me some examples. I have some examples which are rather bizarre. So give multiples of, yeah, so multiples of 3 will not be a convex set. Examples of convex sets. Set of all natural numbers is convex. Set of all real numbers would be convex. The real interval on the number line, any interval on the real number line will be a convex set. Right? Any interval on the real, will any open interval on the real number line be a convex set? It will. Any real interval on the real number line will be a convex set. Right? But suppose now I take the following set. Okay? So think of the set 1, 2. Right? And think of the set, these are two closed sets. Okay? And think of the union of these two sets. 1, 2 is a convex set. 2, 4 is a convex set. The closed set, the convex set. So tell me, what do you think of the union of A1, 2 and 3, 4? Think of this, argue about this, debate about this, right? Let your mind work. I need you to debate. So what we are saying is, if you have A is a convex set and B is a convex set, A union B will not be a convex set. Are you saying that? Okay, so let's argue. So this is A, this is B. So first, A is a convex set, B is a convex set. Is A union B a convex set? A union B is a convex set? Prove it to me. See, what do you mean by saying that A is a convex set? If I take, if X belongs to A, Y belongs to A, lambda X plus 1 minus lambda Y also belongs to A. Right? X belongs to A, lambda X belongs to A plus lambda Y belongs to A. Right? What do you say by saying when Y is a convex set? So think of some Y1 belongs to A, or think of some set B, right? So Y1 belongs to B, Y2 belongs to B. Every linear combination of Y1, Y2 belongs to B. Right? Okay. Now think of points which belong to A or B. So your point X which belongs to A and some point Z which belongs to B, which belongs to A union B. Right? Now are we going to say that a linear combination of X and Z also belongs to A union B?
In this example, we said the region between 1 and 3 you can't take linear combination if you take a combination that will not lie in A union B.
Yeah, but I still want you, what you're saying is right, but I want you to do it more formally. Right? Okay? Sure? Right. And also tell me what it means for budget sets and all that, all those kind of things. Okay, tell me what it means by the budget sets and all those kinds of things. Okay? Right. Okay. Finally, we have to understand two ideas. The boundary of a set. The bounds of a set. Okay? The bounds of a set. Okay? So, if you have a set X, okay? So suppose you have a set S and there is some number, say U, such that U has the property that for every X belonging, for all X belonging to S, U is greater than or equal to X. Right? Okay? Clear? So U is some number which is greater than or equal to every element of X. S. Is U a unique number? No, there could be many such U's, no? Now, among those many U's, if you choose the smallest U, that smallest U is called the least upper bound. Whereas U is just called an upper bound. If you take all the upper bounds which satisfy this property, the smallest of those upper bounds is called the least upper bound. Right? The smallest of the upper bound is called the least upper bound. For example, if you take the set 1, 0, what is the least upper bound for this set? So is 2 an upper bound for this set? 2 is an upper bound, no? Because every element of this set is less than 2. Is 3 an upper bound for this set?
Yes.
Is 1.5 an upper bound for this set?
Yes.
Is 1 an upper bound for this set? Yes, because less than or equal to. So what is the lowest upper bound? 1. You call it the least upper bound. Okay? So suppose I will define a lower bound. Yes, suppose I want to define a lower bound. How will you define a lower bound? The set of all points M, so that every point of X is greater or equal to M, will be a lower bound. Right? Sure? If M has the property that every point of S is greater than or equal to M, then M is a lower bound. For example, in this set, -1 is a lower bound, -2 is a lower bound, -1.5 is a lower bound. And if you take all the lower bounds, the highest of those lower bounds is called the greatest lower bound or the infimum. Right? Whereas the least upper bound is also called the supremum, the greatest lower bound. What is the greatest lower bound here? 0. Right? Greatest lower bound here is 0. Okay? A set which has a lower bound and an upper bound is called a bounded set. A set which has a lower bound and upper bound is called a bounded set. And now we are going to work with a very important idea. At least in R, a set which is closed and bounded has a name. It's called a compact set. Okay, and a lot of our ideas are going to work on compact sets. It's the existence of compact sets which makes things like derivatives, etc. possible, right? So therefore, if you have a closed and a bounded set in R, is called a compact set. A set in R which is closed and bounded. You know what's a closed set? You know what is a bounded set? It's a lower bound and upper bound, right? Okay, such sets are called compact sets in R. Right? So 1, 0 is a compact set. It's a closed set and right? Whereas this is also a bounded set. 1, 0 is also a bounded set. No, and there is also the least upper bound and greatest lower the same, but it's not a closed set. So it's not a compact set. right? And we're going to do some important theorem on the compact sets later on, right? Okay. What we'll do is we'll stop right now. I know we have a lot of time today, but unfortunately I have a meeting scheduled at 12:30, right? So we will have to unfortunately stop today. But is this clear? See, what this is allowing you to do, why is this whole course important, is because, friends, you have learned about a two-dimensional space. All the economics you learnt about was in R2. You learnt the budget line and indifference curve and all that. And you learned that indifference curve is a curve and shapes up and down, and the budget line is a line which goes like this, right? But the real life has a much larger set of dimensions. You need R3, R4, R5, right? So you need to know how to think of the budget line in a larger space. How to think of an indifference curve. How to think of a production function, right? How to think of a production function, for example, which is producing many commodities, which is not a function from labor capital to R. So it doesn't become a curve. Yeah. So therefore, what this is really doing is, it is giving you the basic building blocks of being able to think of the larger economic structures in a more abstract sense, because that's the only tools we have. The simple language that you did doesn't go beyond R2, whereas the real world is a much more complex world. Yeah, so that's the reason why we are actually learning this course. Is this clear? Okay, two things I want to tell you.